Welcome to week 2 of this mini course. We're going to focus on shocks and what happens with shocks today. We're going to talk mostly about planetary impact kinds of problems. Let me start by sharing my screen here. So let's see. We are going to talk today about asteroids and planetary impact. We're only talking about shocks, but we're going to look at the consequences of shocks in the asteroid domain. I've got a bunch of pictures here. Let me just walk through first the people on the bottom. This kind of work is done with a variety of people. I'm showing you here some of the graduate students, postdocs, and colleagues that have participated in the work. So you'll see a bunch of them. You can see Gary live on screen, so he's another. And the work, most of the work I'm talking about today, at some point or the other, has been funded by NASA. Now, the pictures up on top are the ones that are interesting. So I'd like to start with the picture on the top left here. This is another picture of the moon. If you remember when we met the first time last week, I showed you a photograph of the moon. This one is interesting in part because it was taken by James Willingham, who's an amateur astronomer who works out here in Howard County. It's a picture taken in Maryland on May 2nd. So this is the kind of thing you would have seen last week if you'd gone out to take a look. And there's the crater Tycho that we talked about last week. The picture in the middle here is actually a movie. And before I get this thing started, so you see up here, it's asteroid 101955 Bennu. Bennu is the name of the asteroid. This is the number. So this is an asteroid that we have actually visited. That is, a NASA probe visited this asteroid last year. And what I'm going to show you is, first, in this movie, what we thought we would see before we got there. This is a movie taken using essentially a radar telescope. So radar imaging that allows you to estimate what the shape would be. And this is what we thought we'd be visiting. And the picture on the right, this one here, is actually the asteroid itself, the one that we did visit. So here it is. This is actually the asteroid Bennu, the same thing as this, taken from a different orientation. This movie was made while there was a probe orbiting Bennu. The probe itself is called OSIRIS-REx. We're going to talk a little bit about what that probe observed. So this is what we want to talk about. Now, my topic of interest really here is the connection between shocks and the asteroids and the planets, really. So let me first start by recalling what we did in the last session. So the last time around, we were talking about some of the foundations with respect to shocks. And if you remember, we decided or discussed the fact that shocks are typically caused either by an extreme event or an instability. So one of these two is what develops a shock. We're going to talk today mostly about extreme events, not instabilities. Instabilities we'll come to in the fourth class, in the fourth session. And as an example, a movie on the right, taken using a high-speed camera. It's an impact into a rock basalt. The impact is causing a crater. And this yellow line is showing you where the shock waves are as they propagate out. The red line is a different kind of wave called a shear wave as it propagates up. So you can see the impact causes a shock, and the shock then moves up. The shock itself is characterized by a jump and a wave. Remember, we talked about this the last time around. So the jump is propagating through the system. The wave is the speed at which it propagates. The amplitude of the jump, that is how large the jump is, tells you how much damage is going to be caused. And you can see here the bright regions are where the rock is fragmenting. The wave speed determines how fast you move that information through, right? So the shock is what we're thinking about. It's got a wave, a jump and a wave. The jump causes the damage. The wave moves the damage through the system. And some systems will tend to develop shocks while others will tend to dissipate shocks, to spread them out. We're interested today in the systems that develop shocks. All right, so this is what we learned in the last session. So today, we're going to take that idea and really talk about the jump part of it. So we'll put the wave aside for the moment, focus on the jump, and look in particular at the jump that's created by an extreme event, which is planetary impact. So a large-scale impact that creates typically a crater inside the body. You folks know by now that I like poetry. So this is one of my favorites. This is the Rubaiyat by Omar Khayyam. And this is actually the translation by Edwin Fitzgerald. who took some liberties when he was going through the translation, as one of my students who really knew Arabic tells me. But let me just read it to you. So, dreaming when dawn's left hand was in the sky, I heard a voice within the tavern cry, awake, my little ones, and fill the cup, before life's liquor in its cup be dry. So Omar Khayyam was a poet who lived in around 1100 AD, so 1048 to 1131 is what we know. He was also an astronomer. And when he says dreaming when dawn's left hand was in the sky, you folks may be familiar with the idea when we say something is sinister, we're really talking about the left hand. That's where that word comes from. And this is something that is like the false dawn. So dawn's left hand is like the false dawn. And what he was actually talking about is what we call these days the zodiacal light, which is something that looks like the dawn, but which is in the wrong part of the sky. And this is an image of the false dawn that you're seeing here. I'm bringing up this particular poem because it connects to what we're doing today. The zodiacal light, which you can see in the sky if you have a dark sky, is a place where sunlight is reflecting off grains of dust in the solar system. That's really what Khayyam was looking at back then. Okay, now let's think about where the dust comes from. So let's start first with the solar system, just to get a sense of this. I know most of you probably know this already, but some of you are on the younger side, so let's walk through it. So here's the solar system the way in which you might see it, pretty much to scale, not quite. Here's the sun on the left. There's Mercury, Venus, Earth, pretty much the same size, completely different planets. Mars, pretty small. Jupiter, the largest planet in our system. Saturn with its rings. Uranus, Neptune, and Pluto, which we don't really consider a planet anymore. This is a dwarf planet. Incidentally, Jupiter, these four all have rings, but Saturn has the rings that you can see really easily. So this is the solar system as it is. Okay, and our interest is in what happens inside this system. Let me talk briefly about these kinds of planets here. These four, Mercury, Venus, Earth, and Mars, are rocky planets. Sometimes we call them the terrestrial planets. These four are giants. These two are gas giants, and these two are icy giants. So these are the kinds of planets we typically see. Now, this is our solar system. We know now that there are many, many solar systems out there, lots of extrasolar systems, lots of extrasolar planets, and they were all formed using the same processes we're going to talk about today, as far as we can tell, most of them anyway. All right, so let's think about the solar system from a different viewpoint. So we're going to think about impacts. Impacts turn out to be a really big deal in the solar system. So in the early days of the solar system, which is about 4.5 billion years old, what we found, or what we believe happened, was that the giant planets, really Jupiter, Saturn, Neptune, these were closer to the sun than they are today. This is a model for the evolution of the solar system called the Nice model, after Nice in France. That's where it was developed. And then the idea is that a short time after the system was formed, the giant planets came into a resonance and began to move inside the solar system and moved out to where they are now. So they started further towards the sun, and then they began to move out towards where they are now, where they're outside the orbit of Mars, right? As they were moving out, they picked up a number of large planet-sized bodies, parts of the early solar system, and threw them in towards the sun and the Earth. One of those bodies actually hit the Earth. It was probably a Mars-sized body, and the current model for the formation of the moon is that that impact is what actually caused the moon. That's what formed the moon. This is a theory, a model, for instance, developed by Robin Kennop. This was published in Science about 8-10 years ago, where the basic idea is you have a large impact. The impact then generates a spinning set of disks. Eventually, one part of this will spin off and form the moon. There have been various improvements on this model since, but they all have the same basic idea. One large body hitting another, that creates the moon. That would explain why there are some similarities between the chemistry of the moon and the Earth. So impacts are a critical part of the formation of our Earth-Moon system. When you look at the moon, you're seeing something that's a consequence of a major impact. It turns out that impacts actually dominate what happens inside any solar system. So impacts really shape the solar system as it is today. Many of these bodies were thrown in towards the sun when the giant planets migrated up, but some of them were left behind. And the ones that were left behind The ones that are close to us, we tend to call them the asteroids. Okay. Let's talk about the asteroids. So this is a movie here, I got this from Patrick Michel and Marco Delbo, of the 5,000 largest asteroids and their orbits. By no means are these all of the asteroids, it's just some of them, the big ones. The black ones are the asteroids here. Let me run you through the movie a little bit. There's the sun, the big black thing in the middle. The really quickly spinning red thing is Mercury. The green one is Venus. The blue is the Earth. This magenta color is Mars. And way out here, this light blue thing, that's Jupiter. The main belt of asteroids is between the orbits of Mars and Jupiter. And that's where they spin around. All right, so these are the asteroids. Most of them are primordial bodies, but all of them have been hitting each other for many years. And what I mean by primordial bodies is formed in the very early stages of the formation of the solar system. You'll see that there are some asteroids that move in the same orbit as Jupiter, ahead of Jupiter and behind Jupiter. We call these the Trojan asteroids. If you remember the Trojan War, you'll get an idea for why we call them that. All right, so these are the main belt asteroids, okay? So you know the major planets in the solar system, and then you've got these asteroids between Mars and Jupiter. But you've also got a number of them, and you see them down here, that come fairly close to the Earth. We call these the near-Earth asteroids. And here are the larger near-Earth asteroids. Again, these are not all of the near-Earth asteroids, just the larger ones. You see there are lots of them. There are lots of them that essentially share the same orbit as the Earth at some point. So they intersect Earth's orbit somewhere. Most of these near-Earth asteroids only survive for about 10 million years. To give you a sense of scale, so the Earth is about 4 billion years old, right? Most of these asteroids are only around for about 10 million years. These asteroids, the near-Earth asteroids. Because within that time, their orbits are such that they will either hit a planet, or they'll hit the sun, or they'll get kicked completely out of the solar system. That's typically what happens. These near-Earth asteroids are the ones that people typically worry about when they think about asteroid impact on the Earth or things like that. So we're going to think about these near-Earth asteroids. They all tend to be rocky, okay? So we have near-Earth asteroids that share orbits fairly close to us. I should say one thing here. Although I'm showing you these asteroids as these fairly big blobs, they're actually very, very small. Most of these asteroids, if I try to put them on, plot them to the same scale as this picture of the Earth, you wouldn't see them in this kind of a picture. To make them visible, we have to make them big. Okay, now, we started out by talking about shocks. So what does all this with the asteroids have to do with shocks? So the fact is, we have these impacts all the time inside the solar system. Those impacts are what generate shocks. And I have here a movie for you. Oops, I didn't have sound. I didn't realize I had sound. So this is a movie from NASA, from the Lunar Reconnaissance Orbiter, or LRO, showing craters on the moon. This is an area of the moon as the sun rises on the moon. So you can see the border, that sunrise going there, that's the dark side of the moon, here's the brighter side, as it moves across. And you see craters everywhere. Of course, Galileo, when he looked up the first time with the telescope, he saw the craters, and the Pope, of course, was very upset with him at that time, because the idea was that the moon was a perfect body. But you see them all over the moon. And if you think about these craters, and I'm going to stop this there, whoops, let me go back, and look on the right, this is typically what happens when you have an impact event. So imagine this is the moon's surface, or any rocky surface. You have an impactor coming in, which is an asteroid. You create a crater. What really happens is you create a shock wave, which propagates out. Behind the shock wave, you'll get cracks, you get fractured rock. Some of those cracks become so pervasive that you end up with fragments, pieces of material. Those pieces get thrown out into the air if you have an atmosphere. Eventually, they might land back down. One of the really interesting questions is, what happens if you have life on the body and then you kick it out with one of these impact events? Does the life survive during the launch? Will it survive on re-entry? And there is some argument that we could actually move life between Mars and Earth, for instance, through an impact event. If we get the time, we will talk about that. So we have these major impact events which cause impact craters, and those cause shocks. Let's skip the movie. So let's just walk through this movie of how impact craters are formed. This was a movie actually made by Gary Simpson, who's your quasi-TA on this call. So this is a movie made where an impactor is going to come in from the right. It's impacting a transparent material, glass actually. Well, you're taking pictures, these are nanoseconds here. So you're going to come in and take pictures in the microsecond kind of domain. Here comes the impactor, generate the impact. You see the shock waves, those big curved things going up. You see the fracture, the fragmentation. You see ejector, you see pieces flying out. Here's the impactor again. Impact, shock waves out, fracture behind it, ejector being thrown out, the ejector moving far away. In here, you'll have a crater. Here it comes again. Impact, there's the shock wave, and then the damage going out from it. So the jump due to the shock wave is causing the fracture. And the fracture then causes the fragments, which then causes the crater. I'd like to draw your attention to a couple of other things. In this case, we're using a hypervelocity facility in our labs. That's how this projectile was launched. Notice behind it, there are a couple of other projectiles coming by, these two. And you'll see that each of them generates a second impact. What's that second one? So here comes the primary, causes the impact. Here's the second one, it comes through, it causes an impact there. And there's a third one. And if you look carefully, you'll actually see a shock ahead of that third impactor. So you get shocks within shocks in a system like this. So an impact generates shocks. The shocks have a jump and a wave. You can see the propagating wave. The jump causes the fracture. That's our process. All right, so impacts generate shocks. That's the first point. The jump in the shock causes the damage. That's the second thing to remember. The damage creates the fragments, and the fragments then fly away. You see all these pieces flying away? Those are the fragments. If you had gravity, those fragments would fall back down again, and you'd collect them as ejecta. So as pieces of rock on the surface of your planet. So that's the connection between impact craters and shocks. The fact is we see impact craters everywhere that we look. So this is Mars. I showed you this picture the last time around when we were looking at the poem of by Longfellow. This was the same picture at that time. You can see these are all craters. Some are small craters, some are really large, like this big one here, or this large one up there. Okay, so this is Mars. Here's Mercury. So these are pictures taken by the Messenger mission, the NASA Messenger mission. Here's a basin. The basin is basically a very large impact crater, the Radicladi Basin. You can see it has an outer ring and an inner ring. And if you remember pictures of a water droplet dropping into milk or something dropping into the water, you remember the waves? We had that movie the last time around. This is almost as though one of those waves froze in place and there's another one. You can think of it that way. Here's another crater over here, and you can see you actually get a tectonic, you get some geologic motion across this crater rim. So craters on Mars, craters on Mercury, craters on the Earth. This is Barringer Crater in Arizona. You can go visit this. I heartily recommend it. It's quite an amazing structure. It's about a mile or so across here. It's a relatively small crater. But you can go look at it, or you can walk around inside it, if they will allow you. You can actually drive up to it. There's a little road here that gets you up along the way. Really worth visiting this crater. It's only about 45,000 years old, relatively young. All right, so we see craters in all of these. We obviously saw craters on the moon. So craters everywhere. Here is Tycho, the bright crater that I showed you before. This is a movie taken by the JAXA Selene mission, the Kaguya camera really on this mission. And this is the central mountain inside that crater. You are now moving inside the crater. That mountain is think of it as a mile high, a couple of kilometers high. And that's the consequence of the impact. So you have a crater, you have a lot of fragmented material. You see all this dust down here. Some of it has slid down from the mountains. You can move on over. Here is the rim of the crater. So the moon actually has significant gravity. So after you have the impact, the pieces are collected back together and then will collapse according to the gravity, right? Imagine you pour a pile of sand onto the floor, it's going to maintain a certain shape. That shape is determined by the gravity and the friction between the sand and grains. So here, now you're seeing the rim of the crater. You can see there are places where it's collapsed multiple times, and now we're moving along the rim. So these craters can be very large. You can actually have mountains inside the crater, but they are all a consequence of an impact event and the shocks that are generated from the impact event. So, asteroids, impacting bodies, developing impact craters through the process of driving shocks through the system. Now, the fact is we get hit by asteroids all the time. In fact, we as humans, and most of you probably know this, we are actually the legacy of a major impact, which is the Chicxulub impact. So here's the story. We'll try to construct a story for you out of this. The data is a little harder to piece together statistically, but around 165 million years ago, so the theory would go, there was a large impact in the asteroid belt. So one asteroid hitting another generated a lot of fragments. Those fragments then fly apart, but they're moving with some velocity. They get moved away from the primary orbit as a consequence of the impact. One of those fragments hit the moon, and that caused Tycho, the crater that we just looked at. And you can see the big rays of Tycho here. These are the ejecta from the impact. So those pieces that are thrown up and then they fall back down and they give you these rays. Another of those fragments from the major impact ends up hitting the Earth. Now, the impact, the fragmentation in the asteroid belt, we think happened 165 million years ago. The piece that hit Tycho is about 110 million years old. The piece that hit the Earth was about 65 million years ago, which is when the dinosaurs disappeared. You go in and look a little more carefully in that domain, in that region, using something called gravimetric mapping. So basically looking for where you see unusual masses, and you can see sort of the shape of a crater. And this, of course, is what wiped out the dinosaurs. This is our current best model for this. And the fact that the large dinosaurs, the large reptiles went away may have been what really led to the rise of the mammals, and then eventually to us. So these impacts have effects that are very, very far-reaching. 100 million years between the original breakup and the impact on the Earth. That's the kind of scale we're looking at. And just in case you think these impacts only occurred millions of years ago, here is a graphic that I pulled out from this particular website, which is the one that tracks fireballs for NASA. This is through 2020, March 4th. So March 4th of this year. So from 1988 to March 4th of this year, these are all of the fireballs that we have observed in the atmosphere. Some of them have actually reached the Earth. This is the Chelyabinsk impact event, which occurred in 2013. The colors here go by the scale, which is the impact energy, how much energy you're bringing in. If you think about kinetic energy is half mv squared, right? You're coming in at fairly high velocity. For the Earth, you're typically coming in at velocities of 15 to 20 kilometers per second. So if you take the square of that, multiply by the mass, you get lots of energy coming in. Give you a sense of scale, the star, that is the energy level in the Hiroshima nuclear weapon, which is about the same as the scale here. So we've had lots of fairly large bodies coming into us, but most of them burn up in the atmosphere. The atmosphere is a really good protector for us. Mars has a very thin atmosphere, so we see lots of craters. The moon has essentially no atmosphere, so we see craters everywhere. Mercury, nearly no atmosphere, craters everywhere. The Earth, lots of atmosphere. We are significantly protected. We don't see as many craters. And of course, we've got weathering and so forth that runs through it. So we get impacts all the time. Okay. And just so you get a physical feel for this, this is one consequence of such an impact. This is the Chelyabinsk asteroid from 2013. For those of you who remember, this asteroid was observed by a lot of people driving around because it was kind of an early morning event. You could see the fireball, you could hear the explosion in the atmosphere, and you actually developed a shock wave. The shock wave ends up creating all these fragments of glass inside this theater in Chelyabinsk. It's a really interesting thing to think about in terms of shocks. This is the shock wave, not the blast wave. So when you have an explosion, you get both a shock wave, which is propagating through the air, and a blast wave, which is propagating behind it. The blast wave contains usually some chemistry associated with it. The shock wave coming through a building will give you the fragments inside the building. The blast wave typically coming in gives you the fragments outside, just because of the way in which buildings are designed and the way in which the pressure goes in the blast wave. So you can often tell, right, when a blast goes off inside, if you look at pictures after a terrorist attack, a blast goes off in a street somewhere, and you'll see afterwards that there's lots of glass in the street. Not glass in the buildings, but glass in the street. That's usually the consequence of the blast wave. So Chelyabinsk, this is the event. You can see real damage. About 1,000 people were hurt during this. So this is the case where you had an asteroid moving out in the solar system. It has significant kinetic energy that's coming into the Earth. It couples into the atmosphere and actually results in damage on the ground. To give you a sense of how this happened, here are two pictures from this paper by Popova in Science. Here is a piece of the actual asteroid that hit. Inside this piece, you can see lots of cracks. There are actually regions that are shock domains. So these are called shock veins. These are parts of this asteroid. And there's chemistry in here that can tell you something about how the shock went through the asteroid itself. So the asteroid itself sees a shock. This is a calculation of what happens when the asteroid exploded. And you can see the shock waves. You see these rings? These are the shock waves released from the explosion. But this is called an airburst when the asteroid explodes in the air. So that's really what caused the damage, those shock waves coming through. Okay. So what kinds of asteroids do we have out there? This is a set of pictures taken from individual asteroids that we have visited by one probe or the other. This particular poster was put together by Emily Lakdawala, who's a really good science writer of sorts in terms of communicating this kind of work. I strongly recommend you follow her. But here, just look at these asteroids. This is Matilda, 66 kilometers across. You see this big crater on it? Here's Ida, 60 kilometers across. You see these craters? Eros, 33 kilometers long. There's a big crater. Gaspro, Anne Frank, Steins, pretty small. Itokawa, this really little thing, it's only 500 meters. 500 meters is really small. It's the size of a big city block. That's all you've got. And we visited that asteroid as well. These are comets, which are a little different from asteroids in general. They're usually fluffier, more porous. Okay, so these are the kinds of bodies out there. These are the kinds of bodies that might generate an impact. The real question we have, of course, is what are asteroids made of, right? So we know an asteroid might come in, or we might want to go land on an asteroid. Maybe that's where we're going to get material from. What is an asteroid made of? Well, the asteroids are the same things as the meteorites. The meteorites we have on the Earth's surface, that we pick up from the Earth's surface, are pieces of an asteroid that have actually reached the ground. So here is a particular meteorite. This was picked up in Antarctica, and it's one that my group has studied for a little while. It's called McAlpine Hills 88118. Just because this is the place where it was picked up, what we did was we cut this meteorite. And if we cut along these two lines between these two here for part B, you get this piece. Actually, here's the part B. Here's part C. Part C is this piece. If you look, you can see a small black region on the outside. That's the heating that you got when the meteorite was coming through the atmosphere. It comes in really fast, so the heat doesn't get a chance to go inside the body. It doesn't affect most of the meteorite. That comes through. Now we can cut out pieces of this meteorite and we can go measure its properties. We can measure its strength. We can see how strong it is. We can see what it might behave like when you try to break it. And this is something we do, a number of people do for a living. We try to figure out what the meteorite might, what the asteroids might be like. So to show you what it might be like, I have a couple of pictures here. They're both movies. The movie on the left is a real movie taken from a spacecraft called the Near-Earth Asteroid Rendezvous mission. This was a mission run by APL, the Applied Physics Lab. It went to the asteroid Eros, and if I can run the movie, that's the body itself. So you can see this movie was taken in 2000, and eventually the mission actually landed on that asteroid. You can see it has craters on it, small crater, big crater. We actually have simulated what happens to a body like that if it gets impacted, and that's the movie on the right. That's a calculation. And if you watch this, you can see the shock waves propagate through when the impact occurs. What I'm doing here is cutting out 1/4 of the asteroid so you can see what happens inside the body. The colors here are showing you something about the porosity. Blue means it's porous, so you can see there's a region that becomes porous here as a consequence of the impact. And that develops a crater, which is actually this crater here. So you can see how the craters develop during an impact event. So impacts develop shocks, which develop fragments, and then you develop the craters. And you can see the real consequences of these bodies. Okay, so with that background, let me try to bring some things together. So far, we're just talking about impact. But in fact, we have fairly large bodies, and so we have gravity. We should talk a little bit about gravity. So if you think about these bodies here, these asteroids, on most of these, there's significant gravity. Significant meaning you will feel it. But on something like Itokawa, you can jump off and go into orbit. You might even be able to leave orbit in something like Itokawa. So the acceleration due to gravity is very small. The escape velocity is what we say. The velocity it takes for you to leave the body is relatively low in many of these bodies. So if we add gravity to our calculations, you'll see something really interesting. So this is an impact calculation again. We're impacting a large asteroid, 25 kilometers, pretty big, at 5 kilometers per second, which is the speed that you would get in the main belt of the asteroids. So in the main belt, impacts of like 5 kilometers per second. Near the Earth, it's more like 20. You get the impact. The red means you have damaged material. The green means not damaged material. And then the gravity begins to have the pieces collect again on the body. And over time, you've thrown out a lot of fragments, but those fragments recollect on the body. And you can see this. The body now changes shape. It was initially a sphere, but it is no longer a sphere. It's beginning to develop this lobed appearance. You can see down here, there's a central crater. There's a crater there, and you've got material falling all over. If you were now to go land on this asteroid, the surface would be very different because of the impact. And this was the work of Charles Elmire a few years ago. Now, the reason this is interesting is because this is quite different from what we thought was happening. So this is what we used to think happened, that we thought that even the big asteroids were relatively weak. And if they were really weak, then the end result was they'd completely fragment, and then you'd get pieces that are collected purely due to gravity. You'd get those kinds of shapes. Whereas what we think is happening is for a big asteroid, you can even get shapes that are very different. So the strength of an asteroid, a big body, might be very different from the strength of a small body. And this is something we have to worry about in terms of what's likely to be coming at us or what we might want to go land on to get material from. So the big picture with the asteroids is they're not just threats to us. They are really potential value. It's very hard to lift material out from the Earth and take it up into space. But we've got a lot of material already there in the asteroids. We've got lots of minerals there. We've got lots of metal. We've got iron. We may even have volatiles, things like ice and water that we can use out there. So rather than take it from Earth, we just need to get out into space and then go visit these asteroids. Okay, so let me try to bring those ideas together. Impacts can break up asteroids. Gravity, though, can put them back together. And so what that means is you'll have lots of asteroids that are broken up, that creates rubble. But then those rubbles are brought back together. We call that a rubble pile. And then you also generate a lot of dust, very fine fragments. So here's a rubble pile. This is the asteroid Bennu that we started talking about at the very beginning of the lecture. This is a movie taken by the OSIRIS-REx mission. This thing is only a few hundred meters across. These things on the right, these are places that were considered as possible landing sites. You can see lots of rocks on the surface. You see this thing is not a ball because it's not gravitationally big enough to become a sphere. It's spinning, that sort of gives it the shape that you see. And you see rocks all over that surface. This is the kind of thing we might typically see when we go out there. This might be the kind of thing that might come into the Earth as well. Okay. So this creates a really interesting question, which is really what I want to focus on for the next few minutes. Look at all of these asteroids that we've visited. So here's Itokawa, the really small one. JAXA, the Japanese space agency, went to it with a probe called Hayabusa, and they found all these little rocks. The scale here is the same as the scale on this one, which is another asteroid, Ryugu, visited by Hayabusa 2. That's a 1 meter scale, and you see the fragments, the little bits of rock. Here's little bits of rock, lots of centimeter size pieces and even dust. Here's Bennu, the one we just looked at. Bennu is even more interesting in that it was visited by Osiris-Rex. You can see this in Loretta's paper here. If you look at this asteroid, you see these little bright spots here? This is dust on the surface of the asteroid that's actually being thrown off, and it's moving out into orbit. The gravity is so low that bits of the dust just come right off and float into orbit. And we can talk about the different mechanisms why that occurs. So the story here is this: these asteroids have very low gravity, yet they have dust on them. Now imagine I have a low gravity ball with dust on it. I hit it with something else. The dust gets high velocity, it should fly off. And now I have a piece with no dust on it, unless the dust recollects over a very, very long time. The question is, where does all of this dust come from when you have low gravity? And for this, we go back to Longfellow, when you remember from last week's poem. So dust thou art, to dust returnest. This is the idea. So you start out with rubble, you generate dust, and then this dust gets thrown out. So where does the dust come from? There's a final mechanism we want to talk about, and it's called thermal fatigue. And the idea is if you have a rock, a large rock sitting on the surface of an asteroid, the asteroid is spinning. So it sees the sun and then it goes dark. It sees the sun and then it goes dark, like you saw in that movie for the moon. When it sees the sun, it gets hot. When it goes dark, it gets cold. And these rocks, you get them hot and cold, they break because of the temperature cycling. We call this thermal fatigue. It's as though the rock gets tired and breaks apart. And if you go look on Bennu, you see rocks like that are broken apart. We think this is a consequence of thermal fatigue. We can't be sure, but that's what we think it is. So we think we're getting lots of dust on the surface of an asteroid, partly because of impact and partly because of the sun. You're heating and cooling and you generate this dust. And you end up with things like this. So this is Bennu, two different pictures. Beautiful rock down here. You see this with the cracks? And you see all of these. You see how different the rocks look, by the way, depending on the angle of the sun. So here you get these big shadows. Here you see only the little shadows. So these pictures can be really give you a lot of insight. You can see the rocks have different colors, so they're probably made of different things. This rock is much brighter than the rest. Different materials in here. So thermal fragmentation is a big part of the dust on these asteroids. So let me try to bring this together. This is a really nice picture from Moroda, who really were talking about the Ryugu asteroid visited by the Hayabusa 2 mission. This paper came out just last week, May 8th last year, last week. So here's the idea. Here's an initial asteroid. It gets impacted by something. You get shocks and cracks. You generate a lot of fragments. The fragments reaccumulate. You get a rubble pile. And here you get Ryugu. This is that asteroid. A few years later, the asteroid's just sitting there exposed to the sunlight. You get a mechanism called space weathering. The sunlight is basically protons. You end up reddening the surface of the asteroid, allows it to get warm. The warm parts then give you thermal fatigue. You get pieces that fly off. The pieces then recollect. So you get different colors in part because of that. And over time, this develops a shape. Then it gets hit again, separates out, moves back out. Each time it gets hit, it throws more dust into the solar system. So let's go back to Omar Khayyam. So asteroids can be formed by gravity. We saw that. Can be shaped by impact. We saw that. You can disrupt the asteroid by impact, and that generates fragments and dust. Comets, by the way, they generate lots of dust too. When you look at a comet's tail, you're often seeing dust, a dusty tail. The near-Earth asteroids develop dust also by thermal fragmentation because they get hot and cold. That dust then gets lifted off, gets out into space. When Khayyam was looking up at the sky and seeing his false dawn, his dawn's left hand, he was seeing the dust from the asteroids. That's what he was watching. And he was an astronomer. I don't think he made that connection yet, but that's what he was looking at. And the poetry and the astronomy come together really well. Also adds another question here. Can the asteroids waste away? So the idea is, I've been sitting out there and being exposed for a while. I slowly break up. I get dusty. I then get hit by something. The dust gets thrown off. The asteroid shrinks in size. Maybe the asteroids don't even last 10 million years, the near-Earth asteroids. Maybe they waste away faster than that. All right. I want to close with a few implications. So we can go visit these things. So you can go visit these bodies. They're typically going to be fractured bodies. They'll have rough, rocky surfaces. You'll typically go there because you want to access material. You want to use that material for something. You can expect that those rocks will already be fragmented, that the asteroids themselves will be fairly easy to get into in that sense. They're already broken up. A really interesting question is, where can you build a base safely? So suppose you build a base on one of these bodies, even if it's a relatively large one, and it gets hit by something else. What happens at that point? You'll get essentially a moonquake or an asteroid quake that's going to propagate as a shock wave through your system. That's going to shake your base, and you've got to decide whether you could survive that shock. And you might end up with the dust coming through. So I want to leave you with a couple of pictures. So NASA has a mission called DOT, the Double Asteroid Redirection Test. It's NASA's first planetary defense mission. It will launch next year in July 2021. It's going to impact a double asteroid called Didymos. There's Didymos A, here's Didymos B, which is the binary, basically a satellite like a moon. And this is what we think is going to happen. This is the objective of the mission: to impact Didymos B, the moon, generate a crater, and see if we can change the orbit of the moon, of the primary asteroid. And we can measure that using a variety of other systems. There are other satellites, other probes that will go out, as well as maybe Hubble. And this is designed and built by Hopkins, so I'm really proud of this one. Launched in July 2021 with any luck, and getting there in about 2022. All right, so that's what I wanted to say. Next week, we'll be talking about shocks in the human world. Come right back down to a human scale and see what happens there. Next week, we're going to shift scale dramatically. We're moving down to the human scale and looking down at the kinds of things you can touch and feel. So I hope you're prepared for a change in scale. The physics is broadly the same, but the biology and the psychology is very, very different. So we'll get to that next week. Thank you. Look forward to seeing you guys.